Welcome back to the video series. In this video, we're going to be having a look at the Schrödinger equation finally and see how we can implement that numerically on a very in a very simple way. And then I'm going to show you how to evolve it using the Comfit library. As always, if you like the videos, share, like, subscribe, and comment in the sections. That helps increase the visibility of the video. So in the last video, I asked you to try to write the Schrödinger equation on the so-called dimensionless form and put dt psi on the left. So let's have a look at how that works. So here is the Schrödinger equation, and dt psi is the wave function, and this is a function. This is an equation that tells you how the function evolves. So h bar is here, me. I'm going to take that as the electron mass in this case, and then vx psi. Now, the way to make this dimensionless is to introduce these combinations of parameters that will allow us to write the equation in a form which is dimensionless, as I've told you. So we introduce the Hart tree energy, which is h bar over me over a0 squared, where a0 is the Bohr radius, which is around 5 times 10 to the negative 11, or if you'd like 0.5 ångström. So the Hart tree energy is like an energy associated with the electron in the hydrogen state, essentially. So it's given by 4.36 times 10 to the negative 18 joules, or 27.2 electron volts. But the point of this combination of parameters is that if I now divide this equation by the Hart tree energy, I divide both left and right hand side, then I get I get this thing here, where on the left-hand side, I've kept the Hart tree energy like this, whereas in the middle, I have inserted the variables, and then I have divided V by EH. So let's look at this first part here. So the left side of the equation, I can write it like this. So I take H bar and put it under the sign, and then I write out dt psi as the dt, and then I put that inside this parentheses here. And the idea now is that if I take this combination EH over H bar T, I look at what that means is that it's this Hart tree energy divided by H bar, which is 6.62 times 10 to the negative 34 joule seconds. I see that this is, and then T, I see that this is T in units of this number here, 24.2 times 10 to the negative 18 seconds. And so if I define a dimensionless parameter T prime as the time expressed in those units, then I see that the left-hand side just reduces to I d psi dt prime. So by dividing by EH and then redefining the time, I have made the left-hand side dimensionless. And now I do the same trick for this, or the same kind of trick for this combination of variables here. By the way, there is an error here. It should be H bar squared here. Yes. So if I look at this term, here, then I can see that it kind of simplifies a lot. I'm only left with 1 over h0 times dx squared. And when I do the same trick, I take that 1 over h0 in the denominator, and then I put it into this parenthesis of dx and this thing squared. Then I can define a new parameter x prime as x expressed in the Bohr radius to get an expression which is doesn't have any, which is dimensionless, right? So it's x expressed in those units. The same thing with the last term here, V over EH. That's the simplest one because I know that V is supposed to be an energy. I can express that in terms of the Hartree energy. And that gives me V prime, which is just the dimensionless potential as well. And doing all of that gives me this equation here, which is the Schrödinger equation in its dimensionless form. Now, if I multiply this equation by minus I get this equation here. Now I've flipped the sign back and forth. I'm not going to do that. I'm going to have the minus sign be here, and then I'm going to have it be like this for reasons that it's going to make more sense. So I get the Schrödinger equation in its dimensionless form here, and then the thing is that all of these parameters now, t, x, and v, they have this prime on them, and I don't want to keep those around, so I'm just gonna change the definition so that the without the prime is the dimensionless variable, and then I'm left with this equation here, which is the Schrödinger equation in what we call the dimensionless form. And what that means is that time now is expressed in units of the this time here, 24.2 attoseconds. Distances are expressed in terms of the angstrom, in terms of this Bohr radius, so 0.529 angstrom. And the energy or the potential is expressed in units of 27.2 electron volts. And you can read more about this transformation if you click this link here. But the point of this is that whenever someone says, we just set h bar to 1 or we set c to 1, what that actually means is that you're stating something about like what are the physical units of your system. And here I've just made that that connection explicit. So this is the equation that we're going to be working with, dt psi, on the left-hand side. So we're going to go directly into programming in this video. So we're going to take this equation and essentially just implement or try to solve this equation directly using Forward Euler, which is not going to be a very solid method, but it's going to work. And then I'm going to show you how to use the Comfit library, and we're going to have a look at the evolution of a wave packet. So here I have my library. I've installed Comfit. And so let's just start by implementing creating a system. So qm equal to cf dot quantum mechanics. Yeah, I need to import, of course, import Comfit as cf, import numpy as np. Qm is equal to cf dot quantum mechanics, one dimension. Let's stick to xlim between -10 and 10. I think no, actually, yes. So I think to know here when you're doing kind of these like numerical simulations with fields, it's very often a bit of work to find the parameters that give you the expected behavior that you want. It has to do with the stability of the time step and the position and the discretization in space and everything. And so in preparation for this video, I have found parameters that kind of work okay. And so I'm going to use those. So if you think it's strange that these just come out of nowhere, they come from the fact that I've experimented beforehand to try to find limits and steps that kind of work with the system. So we're going to be using -20 to 20 for the limit. And I'm going to set the step length to be 0.2. And then let's just create an initial condition, Gaussian, and we're going to set its width to 1, position to 0, and initial velocity, let's just put it to 1 for the time being. And so now we're going to implement this, the Schrödinger equation numerically. And so what we need to do is we need to calculate this right-hand side, and then we need to increment the psi function with a time step according to the right-hand side of this. So let's start by implementing the right-hand side of this equation. What we do here is that we see that this dx squared is taking the Laplacian or the derivative twice of psi. So the way to do that using NumPy is, or one way to do it, is just take the gradient of qm dot psi, and we're going to take that twice. And also we're going to take it with respect to dx as the spacing in the x direction. And we need to take that gradient one more time. qm.dx. Gradient. So that's this term here, or it's actually this term applied to psi, and then we need to multiply by -1/2. And then also we're going to multiply with v of x. Now, for the moment, we haven't specified what v of x is, but we can do that later. But for now, it's essentially 0. I can show you. Like, the QM object has this property called vx. Well, QM is not defined yet, but it has this property vx, which essentially is the external potential. So we can just use that. So we're going to use plus qm.vx times qm.psi. So that's the second term. And then we need to multiply this whole thing by -i. And -i on the computer is -1j. And from here, we know that this is supposed to be d psi dt. Is this, right? So the way to do a forward Euler very simple integration is to create a loop where we go through for some time steps. So for n in range, let's just do it for 10 time steps to begin with and hope nothing breaks. So for each time step, we calculate the right-hand side of this equation, d psi dt, and then we update the value of psi. So psi is equal to, or qm.psi is equal to qm.psi plus qm.dt multiplied by d psi dt. This is essentially the forward Euler kind of evolution, and we're just using that for this field. So let's create a figure to see how this looks. So I'm going to do fig axis equal to qm dot plot subplots to create a grid, 1 row, 2 columns, and then we're just going to plot the initial condition, qm dot plot complex field, qm dot psi x equal x of 0, and title initial condition. And then after having evolved it for time and time steps, let's just add that as a variable. Then we can, and it's probably realized what I want to do. qm.plot complex field, qm.psi x equal x of 1. After, and let's do after. Actually, I think we can do it like this. After number of time steps. Or do I need the F? Yeah, I need the F format for this to work. Okay, so let's try, see what this gives us. Yes, we need to show the fig, of course, in the end. Right. So here we see that we start with the initial condition, and it's a centralized Gaussian. And after 10 time steps, we see that due to this initial velocity that we gave the function, the whole function has moved slightly to the right. That's essentially what happens. Let's try to evolve for 20 time steps. Hope it doesn't break. Right, so you can see after 20 time steps, it has moved even further to the right. If instead now we set the initial velocity to be negative, we see that after 10 time steps, the wave function has moved a little bit to the left. So let's create an animation, because that's always fun. So we are here. I think I need to. Yeah, right. Sorry. Okay, let's create an animation. And let's not include the initial condition. Let's just have it in here. And the first time we go in, yeah, I think this is correct. So we need to create the figure now. So fig x is equal to this, and then we need to save that function or save the plot. So qm.plot save fig n, and then in the end we need to create tool make animation GIF n. So let's just do that for 30 time steps and see what happens. So now it's creating plots on the left hand side here. Maybe you haven't looked at animations thus, or I did show some animations in the first video, so I suppose it's there. But the way it goes is that essentially I'm just creating a figure. I'm saving the figure here, and then I'm doing this for every point in the loop. And then at the end, I'm taking all those pictures that were produced and putting them together in an animation, which creates a GIF. So here we have it. So here you can see the evolution of the wave function. It's kind of small. Can I? Here, maybe. So here you can see the evolution of the wave function. So this is essentially what the wave function does to, or what the Schrödinger equation does to an initial wave function which has a velocity in the negative x direction, and it expects you as you would behave, it behaves as you would expect. It moves along that velocity. And from this point on, I mean, there are a lot of things you can do. Like, for instance, you could change the velocity to 0 just to see what happens in that case. You can also create a much, or give it a much larger velocity. Let's say we give it a velocity of 3. I mean, all of these things you can play around with now. So that's the evolution of a wave packet. Yes. Now, this way of implementing the Schrödinger equation using a Forward Euler algorithm is not very. It's not a very good way to simulate a field equation. And so in Comfit, there is already a method to evolve the Schrödinger equation, which uses a more advanced evolution scheme, which is called exponential time differencing with Runge-Kutta things. There, you can read about it on the webpage comfitlib.com. But for the purposes, I'm just going to show you how to use it in practice. So you just do the same thing, except that you just write instead of doing this, you can just write qm.evolve Schrödinger, and then just do the number of time steps, 1 time step in this case. And that should probably give us something similar to this. But let's look at the 2 simulations that we made. So this is the one simulation where we didn't where we didn't give it an initial velocity, and we see that the initial wave packet, which is now at rest, it sort of spreads out, which shows you that as time goes on, the initial wave packet becomes less determined in spread. The position of the particle becomes less and less certain the more time moves on. This is the simulation where we gave it a higher velocity, and you can see that it moves to the right faster than the first one where we gave it a lower velocity. Now, if you look very closely at this one, you can see that actually the value of the wave function here goes all the way up to like 30 or 50. And that, of course, is not something you expect, because you expect the wave function to be normalized at all points in time. And so that's not possible when it gets so large. And that has to do with numerical effects. So this is an indication that the Forward Euler scheme that we made is not very good. Let's have a look at the last one. So here it's the same simulation, only now I'm using the evolved Schrödinger method in the quantum mechanics class, and you can see that in this case it doesn't have that same problem with the magnitude getting larger, and we can see that it's moving to the right with a higher speed because we gave it a larger phase gradient, and it spreads out in space as well as it's moving to the right. So I think that was the end of this video. And so what I want you to try to do for the next video is to try to take this Comfit library, make use of this this notebook that we have written, set the Vx variable to be 10 outside of 0 and 1, and then put a Gaussian wave packet inside, give it some velocity, and see what happens. That's the exercise for next time. And until that time, I will wait for you here.